Okay, it is time now to discuss about acid strength and the concept of Ka, or the acidity constant for the acid. As we said before, we're going to stick with the concept of acids as substances that increase the concentration of H plus when added to water, and for bases that increase the concentration of hydroxide ions when added to water. In the case of bases, we're going to use the concept of Bronsted-Lowry, in which the base will increase the concentration of the hydroxide whether the base contains the hydroxide ion or not. Okay, so there are substances that there is no hydroxide around in that formula, but still that substance is capable of increasing the concentration of the hydroxide ion. Same thing goes for acids. But when working in chemical equilibrium, it's easier to work the acids because you always put that hydrogen there. Or at least that is going to be the case for the class. So when looking at acids, and if we are talking about the acidity constant, that acidity constant is an equilibrium constant. And we are looking at the particular case in which we have the acid that is reacting with water, and that we're going to give you the conjugate base for the acid and the hydrogen ion. So one thing that I want you to keep in mind here is that, well, that chemical equilibrium looks like something, but you don't have to always write it in that way. We can even write it in a simpler way. So if you want to be more chemically correct, then we can use HA to represent the acid plus water, and this is in equilibrium with the conjugate base of the acid plus the hydrogen ion. Okay, that's a simpler way to describe the acid-base reaction, or at least for the acid. The base is going to have a similar expression, but it's going to have hydroxide ion instead of the hydrogen. However, for our practical purposes in the class, you are also allowed to use this equation. So you can even say that HA, in presence of water, but we can omit the water, will undergo this sort of reaction. You are basically splitting that acid, not exactly in half, but you're separating into the ions, right? And one of the ions is a specific ion, is the H plus, and the other ion is the anion for the acid, which is going to be the conjugate base. So either one of these two, you can use them interchangeably. So there is no going to be any penalty if you use one or the other. So that's perfectly fine. As such, if this is an equilibrium reaction, then we can write a constant, right? Actually, the acidity constant is going to be H plus times A minus over HA. And then you might be thinking, oh, well, yes, that looks okay, but what happens if we are using this and there is water? Well, the good thing about this chemical equilibrium in the particular case of acids and bases is when you have water in an acid-base equilibrium, is going to be water in the liquid form. And when you have pure liquids or pure solids, then they do not participate in the expression of the equilibrium constant. So we can forget about the water when we write those equilibrium constants. So now that equilibrium constant is a measure of acid strength. Okay, if the constant is really, really large, then you have a strong acid. If the constant is really, really low, then it's a weak acid. So this is the case in which we have a strong acid. The constant is going to be, it's larger than 1, but I don't want you to stick with the value of 1. I want you to see it from the point of view that the constant is large, really, really large. Okay, what does that mean? If the constant is really large and we are looking at this equation, right? If the constant is really large, what that means is that the equilibrium is favoring the products. Okay? the concentration of the products are going to be much larger than the concentration of the reactants. For the particular case of an acid, that actually means that all of the acid that you add to the solution will be present as the ions. Okay, so here, concentration of HA is really, really small to the point that is negligible. So all of the acid is present as the ions. And therefore, if that's the case, then this relationship holds true. The concentration of the acid that you are adding, because, and remember, usually, at least in this case, we will assume that you are extracting one proton out of the acid, at least one proton at a time. So initially, in that first step, in that one step, you remove one proton from the acid, one H plus from the acid. So in that case, for a strong acid, the concentration of the acid is equal to the concentration of the protons. And remember, that also means concentration of H3O plus. Okay, depending on how you are working this. And to be honest, I don't care if you use H plus or H3O plus. I just want you to be consistent. Okay. From 170, you should have memorized this, but here we go again. These are the 6 acids that we consider strong. Strong meaning they completely dissociate. Let me rephrase that. They completely ionize in water. And what that means, if they completely ionize, that means there is no equilibrium. So you don't treat those, it's still part of the concept of acid-base reactions that we're going to discuss, but you don't treat these acids as if they had an equilibrium. So there will not be, well, actually there might be ice tables, but in that particular case for the strong acids, you do just basic stoichiometry. Okay, there will not be an acidic constant you have to work with. Okay, now that case is different when you have weak acids. If the equilibrium constant, if the acidity constant is really small, then we go back here. Then what that means is that the equilibrium is favoring the reactants. So the concentration of reactants is much larger than the concentration of the products. So in this case, now the opposite, not the opposite, but in the first case, if the acid is strong, the concentration of hydronium is going to be equal to the concentration of acid that you're adding. But in this case, if the acid is weak and is partially ionizing, then not all of the acid that you are adding converts to H3O plus. Therefore, the concentration of H3O plus is going to be much smaller than the concentration of the acid that you are adding. Okay, so this goes for weak acids. And for weak acids, the concept is they partially ionize. So some of the original acid is still present once the equilibrium is established. A few weak acids that you should know or should be familiar with, well, we have acetic acid, vinegar. We have carbonic acid. That's one of the main components. That's what gives the fizzle to the carbonated soda drinks. And less common, formic acid, for when you are preserving techniques, you usually use formic acid. The point is, the concentration of protons will not be the same as the concentration of the acid if the acid is weak. Okay, it's going to be the same for strong acids, but it's going to be smaller if it's a weak acid. Okay, we have been sort of covering this already. As I said before, these are the two equations that you can use to refer to acid equilibrium. Because water here is in the liquid form, you don't see water there in the equilibrium constant expression. Okay, you only have the hydronium, the conjugate base, and the acid. Those are only the three main actors in this expression. Okay, and remember, a larger value for the acidity constant means the acid is stronger. Okay, so that's a way in which you can look at that acidity, that strength of the acid, from a more quantitative point of view. A larger Ka, stronger acid; a smaller Ka, a weaker acid. Here we have a table with several Ka values. Do you need to memorize these? Absolutely not. The point that I want you to observe here is that we start with the chlorous acid, and let's look at the values of Ka. So for that one, 1.1 10 to the negative 2, smaller than 1, weak acid. Then 4.6 10 to the negative 4, and then we keep going down. And as you go down here in this list, then the acid is becoming weaker and weaker and weaker. Another measure, it's not another measure, but a different way to express this strength is by using pKa, which it's here on this table, but I'm gonna hold the conversation on the pKa until we are done with ionization of water, which is the next video that you will watch. Okay, so once again, Ka is the equilibrium constant for an acid. It represents how strong the acid is. A larger value of Ka means that the acid is stronger. For strong acids, those that completely dissociate, those that completely ionize, there is no value of Ka, because basically the concentration of acid in equilibrium is 0. And all of the acid is present as the ions, being the conjugate base for the acid and the hydronium ion. Okay? No need to memorize values here, no need to memorize structures here, not even need to memorize formulas here. All you need to know to work any acid equilibrium, the only thing that you need to remember is that Ha in presence of water will go to H plus A minus. Every single acid equilibrium that you can write, that you can work on, no matter what you're calculating, you can express it as that reaction. And that's all you need to know. Okay? So that's it for this.